Sulfonation. So sulfonation is again another interesting reaction, which shown by is shown by the imidazole and thiazole. See, however, reaction takes place at high temperature. Required mercury sulfate certain small amount of because for the reaction sulfonation to take place, and as a catalyst also high temperature. So these are the drawbacks. These are the drawbacks: high temperature, use of mercury sulfate. Mercury is a heavy metal, and that will give you the sulfonation. At oxazole do not undergo sulfonation. And the fifth position, being a more reactive or most reactive, undergo substitution and give you imidazole 5 sulfonic acid. Similarly, if you go for halogenation, so imidazole and alkyl imidazole undergo bromination and highly reactive, being a highly reactive imidazole under form polybrominated imidazole. We can say all the positions are occupied. All the carbon positions are occupied, or we can say brominated for the imidazole. So this is the challenge. Now, if I want only one monobromination, not possible. Even this is taking place at room temperature only. This is taking place at room temperature, and therefore we can say monobromination only cannot possible. We have to get what? The terabromo compound. Fine. So now, so if I want monobromination, this is not possible, not possible, not possible. Right. So what to do then? So if I want this 4-bromo imidazole, so see, don't get confused. What is it in the bracket 4-bromo 5? It means that for this compound. What is the reason? Because this 4-bromo imidazole undergo resonance, and when you number this resonance part, that will give you 5-brom. So it's called as 4,5-brom. Means bromine can be for 4 position for this resonance structure. When you draw another resonance structure, the bromine will be at 5th position. So there is a 4,5-bromo imidazole. If you want 4,5-bromo imidazole, so that we have to go for another method. What is the method? First of all, you do the simple bromination. First of all, do the simple bromination, and then after getting the tribromo compound, you react with sodium sulfite. Sodium sulfite, okay, Na2SO3, heat it. So selectively, 2 and 5th position bromine are replaced, or because Na2SO3 being a reducing agent, it removes bromine and will give you this 4-bromo imidazole or monobromo imidazole. Another monobromination can also be possible if you replace this reaction condition. This bromine acetic acid is replaced because it is really highly reactive and giving tribromo. But if you are using this compound, what is the name of compound? What is the name? 1, 2, 3, 4, 4,4-dibromo cyclohexa 2,5-dione 1, 2, 3, 4, 2, 5-dione. Very simple reagent, especially interesting reagent. So this will give you the monobromo. See, very interesting reaction. By using this 4,4-dibromo cyclohexa 2,5-dinone, okay, cyclohexadienone, that will give you monobromo, the 4-bromo imidazole. This is the reaction, okay. Similarly, like other reactions, thiazoles and do not show bromination, and oxazole definitely will not undergo bromination. But if you put some electron donating groups, thiazole do not undergo bromination easily. It requires certain drastic condition. But if you attach some electron donating group which activate the thiazole, then it may show bromination at 5th position. But if 5th position is occupied, see, so then reaction will not occur. Similarly, 2,5-dimethyl thiazole having the 2 methyl groups attached to thiazole is not undergo bromination because the reason is 2 and 5 positions are really reactive position, active position, while 4th position is not sufficiently rich, electron rich, and hence bromination is possible, not possible at fourth position. However, in the thiazole, only 2,5 are activated, but if the 2,5 are occupied, then that will not give you the bromination product. Fine. Uh, like as we know, oxazole is highly inreactive or less reactive, therefore halogenation is also not possible and not reported for the oxazole. If you go for the next reaction, acylation, the Friedel-Crafts acylation, and we know it should take place at carbon because Friedel-Crafts only for carbon reaction at carbon, alkylation as well as acylation. And like the we say oxazole, Friedel-Crafts acylation is not reported, or we can say unknown for azoles. Very interesting sentence. What is the reason? The reason is very simple. That because azoles contain nitrogen, all azoles contain nitrogen, and when you react to the Friedel-Crafts acylation, when you provide the condition of Friedel-Crafts acylation, जब हम इसकी condition provide करते हैं, तो what is the condition? Anhydrous AlCl3 and some acylated benzyl chloride or methyl acetyl chloride. तो क्या होता है? नाइट्रोजन का लोन पेयर है ना, that will combine with the Lewis acid and will form the some complex, and this way it will lock the reaction. When reaction is locked, it will not form the product, and therefore acylation are not reported for the azoles compounds. Okay. However, it is possible that some imidazole substituents undergo this reaction, and the reaction will form definitely give you the products. Okay, definitely give you product, but imidazolonium halides. Okay, so one reaction is reported, but with having the some groups there is a methyl or nitrogen. Okay, so when you hit it with this acylation, so but here it is not, it is replaced by the catalyst of Lewis acid is replaced by the strong base, and only then acylation is possible at particular position. So first it will go nitrogen, and then it will migrate from this to this position, and you get this. But here again, Friedel-Crafts catalyst is not employed. Very why? Because if you use the Friedel-Crafts catalyst, that will damage the reaction or reactants, and reactants will not undergo into transformation or will not form the product because of complex formation. But if you change the catalyst or if you use the base, strong base, that will give you the first of all acylation nitrogen, and then it will migrate to the carbon. Very interesting reaction. Another reaction is what? Replacement of hydrogen. So at two positions, or position number 2 of azoles, when undergoing different nucleophilic substitution reaction, and few of these we have seen just now, nitration, sulfonation, these are nothing but the replacements of hydration. So that will give you the uh, sulfonation and nitration, acylation. But if the halogen is present, hydrogen is there, okay, but if halogen is present at two positions, and remember this is a very interesting reaction. Okay, this is a very interesting reaction for azoles. So when uh, halogen is present at second positions, and if you react such compounds with the some special compounds, that is what the nucleophile. See here, this one. This is a very important, very interesting compound. Sodium phenyl sulfide. Okay, yes, or we can say phenoxide, phenoxide, similarly sodium phenyl sulfide, sodium phenyl sulfide. So this is a very strong nucleophile. It will attack here, and this will give you this substitute products. Okay, similarly, if you take oxazole at the two positions, chlorine or any bromine, any halogen atom, and if you react with this same compounds having the strong nucleophile like nitrogen, and heating is required, and this nitrogen lone pair attacks here, and you will find that chlorine will be replaced here, This is sulfur is negatively charged. This will attack here and this will go out. And in the both the cases, this is nothing but nucleophilic substitution reaction will be observed for these reactions. Similarly, the next important reaction is what the metallation reaction. Carbon metallation means what is when we use azoles, thiazoles, imidazoles, or we can say oxazoles, that will give you some metal carbon bond formation. For this, we require the strong base, that is the lithium, butyl lithium. And when you react with thiazoles or oxazoles or imidazoles, but that nitrogen of imidazoles must contain some alkyl groups, not NH. Okay, so C2 position and 5 positions are highly reactive, and hence the reaction will give you the lithiation or carbon metallation. The formation of carbon metal bonds will be observed. You see here, n-butyl lithium, this proton at second position abstracted at -78, and when you react with trimethyl chlorine, so silicon is what is the metallite. So you see carbon metal bond formation takes place. Similarly, when you react this compound with again anisotropy lithium, so what you will find? You will find that this will abstract proton from here, and this Si3 migrate here, and this second position will catch the or we can absorb the protons from water. Okay, so we can see here that the compared to 215 position, 5 position is highly reactive, and you can see here for this transformation also, this 5 position is a migration of this time methyl group takes place at 5th position because it's a very reactive positions. Right? Okay. See, one more reaction is there before you for oxazoles. This was for imidazole. This for oxazoles at second position at inbutyl lithium and trimethyl chloride. Similar observation will be there. So trimethyl, so carbon silicon bond. So you can see a metallation is possible. Fine. So the next reaction is what? A reaction with oxidizing agents. Okay. So all the azoles, they are resistant to oxidative breakdown. Okay. However, few reactions are reported, that is for thiazole is more reactive than imidazoles and then oxazoles. So oxazoles are not reactive at all. So in we will see how the oxidizing agent will react with the thiazoles and imidazoles, and how they form and what is the product. N oxide is the product. Okay, and then we'll go for the N oxide formation and its reactions. Okay, in the next lecture.